In this podcast, we're going to go over the enzyme substrate complex in more detail, and we're going to talk about how enzymes function. All right, let's talk about how enzymes work. When we have an enzyme catalyzed reaction, the enzyme is a protein that is functioning as a catalyst, and it's going to react with a substrate. So think of a substrate as being similar to a reactant in a chemical reaction. So substrate is your starting material. And the substrate is going to bind a special site on the enzyme called the active site. And the active site of an enzyme is kind of special. There, in that location, there may be intermolecular forces or maybe a hydrophobicity or hydrophilicity, depending on your substrate, that's going to attract that substrate into that specific site to make a bond so that the enzyme can then wrap itself around the substrate and give it a certain set of conditions in order for that reaction to proceed that it wouldn't normally have without the enzyme. So once your substrate binds to the active site, we call it an enzyme substrate complex. Once the reaction is complete, the enzyme opens up, releases the products, and in this case it looks like we broke maybe a decomposition. We broke our substrate, our single reactant, into two different products. It releases it. Notice that the enzyme goes back to the same shape it started with. It's ready for a new substrate to come in and bind and to catalyze the next reaction. So think of the active site as being the place on the enzyme where there is contact with your substrate and where your reaction is going to occur. All right, so we discussed this a little bit on the last slide, but let's go into a little bit more detail with sucrase. So you have an enzyme, you have a substrate. They come together, the substrate binds to the active site, you form an enzyme substrate complex. The enzyme does its reaction, releases the product, and reforms to the original shape of the enzyme, so it's unused in the reaction. Let's look at sucrase. It's one of those enzymes that has the old naming schemes that catalyzes the disaccharide sucrose breaking into two monosaccharides. So in the presence of sucrase, the sucrose gets broken into glucose and fructose, and sucrase remains unchanged. When they are bound together, they are in an enzyme substrate complex. So let's take a look. We have sucrose right here. It is going to enter the site of sucrase, so your substrate is going to bind to the enzyme. The enzyme kind of hugs that sucrase, and it is able to provide those internal conditions that we need for that disaccharide to be broken into two monosaccharides, and that's the enzyme substrate complex. Once that enzyme substrate complex has catalyzed the hydrolysis of your disaccharide into two monosaccharides, and you have now products, those products are released to be used elsewhere, and I reform the active site that is specific to sucrose, and I can take on another disaccharide. I just want to take a quick second and show you a space filling model of what an enzyme looks like with and without a substrate bound to it, because it is kind of neat to see. So here we have an active site for an enzyme that binds glucose, and there's our little glucose substrate. I don't know what this does to the glucose, and I don't care, but once that glucose enters the active site, the enzyme binds around it and it creates those internal conditions that are needed for whatever reaction it's trying to do. And I always like to think of this as like a little bear hug, just completely engulfs the substrate and allows for that reaction to happen. But it's kind of neat to see it in a space filling model so you can get a feel for the 3D aspect of these enzymes. So we used to think that it was one enzyme, one product. So the specificity of an enzyme for its substrate and vice versa is a 1-to-1 ratio, so that only a single enzyme could catalyze a single reaction for a single substrate. Enzymes do have to be pretty specific. However, now we're starting to see that that may not be as cut and dry as we originally thought. So there's two theories for why and how enzymes are so specific to their substrate. The first is called a lock and key. In this, your enzyme is going to fit with the substrate similar to how your house key fits into your door and your door only. So the enzyme is not able to fit with any other substrate. It's not able to catalyze any other reaction because of that. So think of it as one key, one door that it unlocks. It is that specific. In this case, your active site has to exactly match your substrate. So if you had another substrate present, your enzyme's not going to interact with that because the substrate cannot fit into the active site of the enzyme, just like someone else's house key won't fit into your door unless they live with you. Bad example. In an induced fit, the induced fit theory of enzyme specificity tells us that the enzyme can sometimes be a little more flexible. It's not as rigid as what we originally thought. And therefore, the enzyme can alter its shape just slightly and just slightly change the shape of the active site so that that single enzyme can catalyze a much wider variety of similar substrates. Now, you can't just take a wildly different reaction and substrate and expect the same enzyme to do it. The substrates are still going to have to be pretty similar, but there's a little bit of flexibility as to which substrates can bind to that enzyme. So it's not necessarily a 1-to-1 ratio of enzymes to substrate. Maybe you have one enzyme that catalyzes 2 or 3 different reactions with 2 or 3 different yet similar substrates. All right, so here we're seeing the lock-in key and the induced fit theory side by side, and it's a little tricky because it's a little nuanced and it's not super obvious, so follow me for a second. So the top is a lock-in key, where your shape of your active site exactly matches the shape of the substrates. So my 2 substrates are going to bind perfectly into their perfect fit active sites. It is made for these 2 substrates. They form an enzyme substrate complex while they're together, and a product is released. Notice that we reform that active site that only fits those 2 substrates perfectly. In an induced fit model, your enzyme doesn't. That's a bad color. Okay, none of the colors are great for all the things I have going on, but your active site does not perfectly match what the substrate should be binding. Instead, it's a little bit more flexible, so it's actually able to take on the exact same substrates that we used before in this reaction, and it's able to mold its active site around those to catalyze that reaction, and we still wind up with the same product. But the difference is my active site is able to adjust a little bit or flex just a little bit so that it can handle 2 different types of reactions or 2 different substrates.